Hello and welcome to DCACM's second webinar presentation. I'm the DCACM Chair, Shahmaz Kamberi. Just want to start out by introducing the board. The board consists of Catherine McClintock, Vice Chair and Secretary, Mike Celera, Treasurer and Programs Chair, and Amar Zumkwala, Member at Large. The DCACM is the DC area chapter of the Association of Computing Machinery. It's a professional association for computing professionals and students. It has a broad membership, over 100,000 members internationally. The organization's mission is to create professional development opportunities for our members. If you're interested in becoming a DCACM member, please join us in our meetup.com site at meetup.com/ACM-DC. We have 661 technical peers. Just to give you a quick announcement, our next webinar would be on May 2nd, and our last webinar in this web series will be on June 6th from 6:30 to 7:30 p.m. Eastern. If you want to present in the DCACM web series, please email skamberi@dcacm.org. If you want to present on-site for DCACM, please email mike@dcacm.org. We would like to give a special thanks to our presenter today and also to the Washington, D.C. Metro DeVry University for providing us the Adobe Connect environment. All right, now let's begin the presentation. This presentation is the Mathematical Theory of Computer Instructions and Statements, presented by Dr. Douglas Maurer. Professor Maurer received his bachelor's degree in mathematics from the University of Chicago and his master's and PhD in mathematics from Berkeley. He was for over 30 years on the George Washington University faculty. He has written 6 books and has almost 200 published papers, mainly in the mathematical theory of computer science. Because this is a pre-recording, I have here listed Dr. Maurer's email address. It's maurer@email.gwu.edu. After you've watched this recording of this presentation, if you have any questions, please feel free to direct your questions to Dr. Maurer at the email address provided. Dr. Maurer, you may now start your presentation.
Hello. I'm Professor Maurer, and I'm a retired professor from George Washington University. This presentation is on the mathematical theory of computer instructions and statements. Next slide. Mathematics, as it is studied by mathematicians, is made up of various specialty areas. Some of these are functional analysis, partial differential equations, mathematical logic, measure theory, Hilbert spaces, Riemannian manifolds. One mathematical specialty area is known as algebra. Mathematicians in that specialty area are known as algebraists. Algebra in this sense is completely different from the algebra that we all learn in high school. It is composed of mathematical theories. Some of these theories are the theory of integral domains, field theory, ring theory, group theory, abelian group theory, semigroup theory. When I was an undergraduate, I learned the elements of all these theories and decided to become an algebraist. When I was in graduate school, I decided that there ought to be a computer theory as well as all these other theories. All my life I've been working on computer theory, and that is what I will present to you today. In order to do that, I need to start by showing you what a theory is. As an example, I will use group theory. I need to assume that all of you have studied sets and all the usual set operations. Intersection, union, X is a member of A, X is not a member of A is contained in B, A contains B, a Cartesian product, A cross B, the empty set, and the like. Also, function notation. F goes from set X to set Y, and the terms one-to-one onto composition, De Morgan's laws, and the like. If you haven't studied these, you're welcome to continue with the webinar, but there will be a lot that you probably won't understand. Next slide, please. First, I will explain what a group is and show you various groups and group theorems. And then I will explain why groups are important. So, a group is a set G together with a binary operation cross on G such that 4 laws. Number 1, if X is in G and Y is in G, then X cross Y must actually be in G. This is called the closure law. Number 2, X cross Y and that much cross Z equals X cross the quantity Y cross Z. And that must be true for all X, Y, and Z in G. This is called the associative law. Number 3, there exists E in G such that E cross X equals X cross E equals X for every X in G. This is called the identity law, and E is called the identity of the group. And finally, 4, for every X in G, there exists Y in G such that X cross Y equals Y cross X equals E, where E is the identity of the group. This is called the inverse law, and Y is called the inverse of X. These are called the group axioms. Large numbers of sets, together with their binary operations, satisfy these axioms. For example, the set of all integers is a group where cross is ordinary addition of integers. Thus, number 1, if X and Y are integers, then X plus Y is always an integer. That's the closure law. Number 2, X plus Y and then that much plus Z equals X plus the quantity Y plus Z. And that is true for all integers X, Y, and Z. And that's the associative law. 3, there exists an integer E such that E plus X equals X plus E equals X for every integer X in G. That's the identity law. In fact, X is 0. E is 0, excuse me. That's a bug. E is 0. So 0 is the identity of this group. And finally, for every integer X, there exists an integer Y such that X plus Y equals Y plus X equals 0. And that's the inverse law. In fact, Y is negative X. So negative X is the inverse of X. Now, more groups. The set of all rational numbers is a group. The set of all real numbers is a group. The set of all complex numbers is a group. In all these cases, cross is ordinary addition. Next slide, please. Now, completely different kind of group. The set of all rational numbers other than 0 is a group where cross is ordinary multiplication of integers. So, number 1, if X and Y are rational numbers other than 0, then XY is always a rational number other than 0. That's the closure law. Number 2, XY times Z equals X times YZ for all rational numbers X, Y, and Z other than 0. That's the associative law. There exists a rational number E with E unequal to 0 such that EX equals XE equals X for every rational number X unequal to 0. It's the identity law. In fact, E is 1 this time, not 0. E is 1. So 1 is the identity of this group. And for every rational number X with X not equal to 0, there exists a rational number Y with Y not equal to 0, such that XY equals YX equals 1. That's the inverse law. In fact, Y is 1 over X. So 1 over X is the inverse of X in this group. More groups of that kind. The set of all real numbers or all complex numbers other than 0 is also a group with cross being ordinary multiplication. Next slide. Oops, I think you skipped one.
Sorry.
Can we go back for a moment? That happens sometimes. No, that's right. You're okay. If Fx is any non-empty set, then the set of all one-to-one onto functions f going from x to x is a group, with cross being the composition operator circle on functions. That is, for any functions f and g, we have f circle g equals h, where h is defined by h of x equals f of g of x for all x in the set x. Thus, number one, if f and g are one-to-one and onto, then f circle g is also one-to-one and onto. That's the closure law. 2, f circle g and that much circle h is equal to f circle the quantity g circle h for all one-to-one onto functions f, g, and h from x to x. That's the associative law. Number 3, there exists a one-to-one onto function e from x to x such that e circle f equals f circle e equals f for every one-to-one onto function f. That's the identity law. In fact, e is the so-called identity function defined by e of x equals x for all x. And this function is in fact one-to-one and onto. And number 4, every one-to-one onto function f has an inverse function g with f circle g equals g circle f equals e. And g is in fact one-to-one and onto. I didn't see that on the presentation, but in fact it's the usual inverse. If f of x equals y, then g of y equals x, where g is the inverse of f. Here we go. The set z sub n, which is the set of the numbers 0, 1, 2, 3, 4, and so forth, up through n minus 1, that set is a group with I circle j being I plus j mod n. Thus, number 1, if I and j are in that range between 0 and n minus 1, then I plus j mod n is also in that range between 0 and n minus 1. It's the closure law. Number 2, I plus j mod n plus k mod n is equal to I plus the quantity j plus k mod n for all integers I, j, and k in the given range between 0 and n minus 1. That's the associative law. This one is rather tedious to prove. Number 3, the identity of this group is again 0. Number 4, now it's a little bit different here. The inverse of k is n minus k. Since k plus n minus k mod n is n mod n, and that's 0. And there are dozens more examples. Now, why is all of this important? It is important because of group theory, which consists of thousands of theorems, all of which are proved using only the axioms. Therefore, they hold automatically for all possible groups. Here is an example. It's called Lagrange's theorem. Suppose that G is a finite group, that is, a finite set G having n elements with an associated operation cross. Suppose that G prime is a subset of G, which is also a group under the same operation cross, and we call G prime a subgroup of G. Then n must always be a multiple of the number of elements in G prime. The point is that the proof of this theorem depends only on the 4 laws: closure, associative, identity, and inverse. Therefore, it automatically holds for all finite groups. This is the power of a theory, that any theorem in group theory, once it is proved using only the 4 laws, is automatically true for all groups. So that's a theory. Now, what is computer theory? Let's be informal first. At any time during the running of a computer program, there is a current state. If you've ever studied finite automata, you know about the state of an automaton, which is typically a small integer. The state of a computer program, P, is different, though. It has to encapsulate the current values of all variables of P. How do we express this mathematically? Let M be the set of all variables of P, that's the memory of P, and let B be the set of all their values, which we sometimes call the base set of P. Then, a state of P is a function S from M to B. If X is a variable of P, so that X belongs to the memory M, then S of X is its current value, so that S of X belongs to B. Note that P might have variables of many different types, real, integer, Boolean, and so on. Then B has to contain all possible values of all these types, real numbers, integers, true and false, and so on. Now, let I be a statement of P. What is I mathematically? When I is executed, there is a current state S. After I is executed, there is a new state S prime, which depends on I and on S. Thus, I must be a function such that I of S equals S prime. Therefore, we express I mathematically as a function from D to D, where D is the set of all possible states of P. How do we characterize D, then, mathematically? First of all, not every function from M to B is necessarily in D. For example, if X is an integer variable, then we don't want S to be in D if S of X is a fraction. Thus, D, therefore, is merely a subset of the set of all functions from M to B. A computer, then, consists of M, B, D, and some statements like I. What are the axioms that D has to satisfy? Axiom 1 says that we can always combine any two states, S1 and S2, in D, into a new state, S3, which is like S1 on some variables and like S2 on all the other variables. And this new state, S3, will always be in D. Formally, if M prime is contained in M, and S1 and S2 are contained in D, then S3 must be contained in D, where S3 of X equals S1 of X for X being in M prime, and S3 of X equals S2 of X otherwise. Another way to formalize this is to say that S3 restricted to M prime equals S1 restricted to M prime, and S3 restricted to M minus M prime equals S2 restricted to minus M prime. Here, M minus M prime is the set of all elements of M that are not in M prime. And S3 vertical line M prime is the restriction of S3 to M prime. That means if S3 is a function from M to B, and S3 prime is the restriction, S3 restricted to M prime, then S3 prime is a function from M prime to B, where S3 prime of X equals S3 of X for all X in M prime. There's a good reason for this axiom, but we will not be able to understand it until close to the end of this webinar. We shall derive axiom 2 below, but first, as we did with group theory, we give several examples of computers in this sense. Number 1, let M be a finite set of bits. Let B be the set consisting of 0 and 1. And let D, this time, be the set of all functions, S, from M to B. Then NBD is a computer. Every state of this computer is a specification of either 0 or 1 for every bit in the memory M. Example 2, suppose that a variable x has type ta. The set of all values of type ta will be referred to here as the type set of x. Note that in some programming languages, such as Ada, two variables of different types can have the same type set. Hence, in this presentation, we always refer to type sets, not simply to types. Now, let M be a finite set of variables, each of which has some type set, and let B be the union of all these type sets. Let D be the set of all of those functions from M to B, such that S of x is always in the type set of x for every x in the memory. Then MBD is a computer. Number 3, a type set can be either ideal or actual. For an integer variable, the type set could either be all possible integers, that's the ideal case, or only those integers which fit into a computer word, that's the actual case. For a real variable, the type set could either be all possible real numbers, that's the ideal case, or all possible floating point numbers, the actual case. Different computers MBD arise from different choices here. Suppose now that P is a program written in assembly language. In that case, I is what is usually called an instruction, which is why I use the letter I to mean a statement. We will also define the input region and the output region of every statement I. So let MBD be a computer and let U and V be variables, that is, elements of M. Let I be a statement that sets U equal to U plus V. Remember now that I is a function from D to D, where D is a set of functions from M to B. Specifically, I of S equals S prime, where we define S prime as follows. S prime of U equals S of U plus S of V. And for all Z in the memory other than U, we have S prime of Z equals S of Z. We want to associate with I two subsets of M. First of all, the input region of I, or IR of I, and that is the region where I takes its data from. In this case, the set consisting of just U and V. And the output region of I, or OR of I, and that is the region where I puts its result. In this case, the set consisting of just U. How do we define IR of I and OR of I? The definition of OR of I is easier. A variable x is in OR of I if it can be changed when I is executed. Formally, x is in OR of I if and only if there exists a state S in D such that if S prime equals I of S, then S prime of x is not equal to S of x. For example, let S be such that S of U is 3 and S of B is 5. Then after I is done, we have S prime of U equals 3 plus 5, or 8, and S prime of V is still 5. We've added 3 and 5 to get 8, which is the new current value of U. Can we move this up here because it is not... There we go. Thanks. But the new current value of V is the same as its old current value. It wasn't changed by I. Okay, now, next slide. This shows that U is in the output region OR of I, while V is not. And by the way, if the output region of I is the null set, then I is the function such that I of S is in S for all S. How about the input region, IR of I? A variable x is in IR of I if it makes a difference what the current value of x is. Formally, let S1 and S2 be two states in D that are different only on x. That is to say, S1 of x is not equal to S2 of x, but S1 of z is equal to S2 of z for everything else in the memory other than x. This is supposed to make a difference. How do we express this? Let S1 prime equals I of S1, and let S2 prime equals I of S2. Then S1 prime and S2 prime have to be different somehow, but now we need to be careful. We can't just say that S1 prime is unequal to S2 prime. That would happen all the time. In fact, let I be the identity function. I of S equals S for all of S in D. Then we always have S1 prime is unequal to S2 prime. In fact, S1 prime equals S1, which is unequal to S2, which is equal to S2 prime. We could try saying that S1 prime of Y is unequal to S2 prime of Y for some Y other than X, but that doesn't work either for a rather complicated reason. To see the reason, let us consider a statement I that adds 1 to K, that is K++ in Java or C++. We have I of S equals S prime, where S prime of K equals S of K plus 1, and S prime of Z equals S of Z for all Z other than K. Now, here OR of I, the output region of I, is clearly the set containing just K, because I changes K and cannot change anything else. What is the input region, IR of I? We would like that also to be the set of just K, because changing K makes a difference. However, it makes a difference only on K. So K couldn't be an IR of I, because if it were, I would have to make a difference somewhere other than K. The right definition is that S1 prime of Y is unequal to S2 prime of Y for some Y in the output region, OR of I. Formally, X is a member of the input region IR of I if and only if there exist S1 and S2, both of which are in D, and there exists Y in the output region, OR of I, such that S1 of Z equals S2 of Z for all Z in M other than X, but S1 prime of Y is unequal to S2 prime of Y, where S1 prime and S2 prime were defined as before. Now, if the memory M is infinite, another problem can arise. For the moment, let D be the set of all functions from M to B. Let X be one specific variable in M, and let S sub 0 be one specific state in D. Now define I as follows. I of S equals S prime, where S prime is defined as follows. S prime of X equals 1 if S of Z is unequal to S sub 0 of Z for an infinite number of variables Z in the memory M. S prime of X equals 0 if S of Z is unequal to S sub 0 of Z for only a finite number of variables Z in M. For all other variables, S of Z equals S sub 0 of Z. Here, the output region of I is the set consisting of just X. But what is the input region? It would seem that we have the paradoxical conclusion that the input region of I is the null set. In fact, Let y be any variable in M. Let S1 and S2, which are in D, be such that S1 of Z equals S2 of Z for all Z in M other than Y. And let S1 prime and S2 prime be defined as we did that before. Then, if S1 prime of X equals 1, then S1 of Z is unequal to S sub 0 of Z for an infinite number of variables Z in M. But then also S2 of Z is unequal to S0 of Z for an infinite number of variables Z in M. So therefore S2 prime of X is also equal to 1. If S1 prime of X equals 0, then S1 of Z is unequal to S sub 0 of Z for only a finite number of variables Z in M. But then also S2 of Z is unequal to S sub 0 of Z for only a finite number of variables Z in M. So therefore S2 prime of X equals 0. In either case, S1 prime of X equals S2 prime of X, and thus X is not in the input region of I. And because that's true for any X, we get that the input region of I is the null set. The reason this is paradoxical is that the value of S prime of X depends informally on the values of all the S sub Z. Therefore, all the variables in M ought to be in the input region. How do we resolve the paradox? We don't want to outlaw M being infinite. We can require, however, that if M is infinite, then a statement I cannot change the values of an infinite number of the variables of M. Informally, this is because otherwise I would run for an infinite amount of time and the program P would hang up. Suppose now that when P starts, S sub 0 is the starting state of P. Every statement of P changes no more than a finite number of variables of P. Therefore, no matter how long P runs, every state of P differs from S sub 0 on only a finite number of variables. Now we can see how to resolve the paradox. We were assuming that D was the set of all functions from M to B. But in the running of any program, any state will be in a smaller d, namely the set of all functions from M to B such that S of Z is unequal to S sub 0 of Z for only a finite number of variables Z in M. The way to resolve the paradox is to require this of every possible D. We can formulate this in an equivalent way. If S and S prime are in D, then S of Z is unequal to S prime of Z for only a finite number of variables Z in M. Mathematicians abbreviate this as follows. If S and S prime are in D, then the set of all Z in M such that S of Z is unequal to S prime of Z is a finite set. This becomes axiom 2 of a computer in the mathematical sense. Now we come to the first major theorem of computer theory. Informally, suppose that the states S1 and S2 are the same on the input region of I. Then I of S1 and I of S2 are the same on the output region of I. Formally, Theorem 1, let I be any statement. If S1 restricted to IR of I equals S2 restricted to IR of I, and S1 prime and S2 prime are defined as we always have, then S1 prime restricted to OR of I equals S2 prime restricted to OR of I. This would seem to follow immediately from the definitions, but it doesn't. In fact, it isn't even necessarily true. unless axiom 1 and axiom 2 both hold. We will now prove it, however. No, yeah, good. We will start by restating the theorem. The theorem is equivalent to stating that the input region of I as a subset of M has the input property, defined as follows. Definition: a subset M prime of M is said to possess the input property IP of I if S1 restricted to M prime equals S2 restricted to M prime and S1 prime and S2 prime defined as before, if all of these imply that S1 prime restricted to OR of I equals S2 prime restricted to OR of I. In order to prove that IR of I, the input region of I, has the input property, we first state three general lemmas. Unfortunately, this evening we won't have time to prove these, but we'll state them at least. Lemma 1. If M prime and M double prime are two subsets of M, each of which has the input property IP of I, then the intersection of M prime and M double prime also has the input property. Now there's a corollary to this, that the intersection of any finite number of subsets of M possesses the input property if each of these subsets possesses the input property. And that follows from the lemma by applying it successively. Lemma 2, if M prime possesses the input property and M double prime contains M prime, then M double prime also possesses the input property. And lemma 3, IR of I, the input region of I, is the set of all X in M having the property that the set of all Z in M other than X does not possess the input property. Now with our three lemmas and our one corollary, we can proceed to prove our theorem. We noted before that our theorem was equivalent to stating that IR of I has the input property IP of I. This is what we shall prove. Let us first assume that M is finite. We will take up the general case later. Okay? Let M1 be the intersection of all subsets of M which possess the input property, IP of I. Since we are assuming for the moment that M is finite, there are only a finite number of these subsets. By the corollary above, M1, that is, the intersection of all of these, also possesses IP of I. We now show that M1 equals the input region of I. This will prove our theorem because then IR of I will possess IP of I, which, as we said before, is equivalent to our theorem. By lemma 3 above, M1 equals IR of I is equivalent to saying that M1 is the set of all X in M such that the set of all Z in M other than X does not possess IP of I, the input property. So let us prove that. First, we note that the set of all Z in M other than X may be written as M minus the set containing just X. M minus the set containing just X is the set of all elements of M that are not in that set, in other words, the set of all elements of M other than X. So we can rewrite what we have to prove as the following. M1 is the set of all X in the memory such that M minus the set consisting of just X does not possess the input property. Suppose first that M minus the set consisting of just X does possess the input property, then X would not be in M1. In fact, we have to prove that X is not in M1 if and only if M minus the set containing just X possesses IP of I. An if and only if proof like this has to be proved in both directions. So let us do that. First direction, suppose that M minus the set consisting of just X possesses IP of I. Then M minus the set consisting of just X is one of the subsets whose intersection is M1. Therefore, M1 is contained in M minus the set of just X. But that means that X cannot be in M1. So that takes care of the proof in that direction. Now we go in the other direction. Suppose that X is not in M1. Since M1 is the intersection of all subsets of M which possess the input property, there must be some subset of M, call it M2, possessing the input property to which X does not belong. Since X does not belong to M2, we must have that M minus the set consisting of just X contains M2. But M2 possesses the input property. By lemma 2 above, therefore, M minus the set of just X possesses the input property. This would complete the proof except for one point which we postponed earlier. Suppose that M is infinite. What happens then? Well, we said that M1 is the intersection of all subsets of M which possess the input property. However, this time there are an infinite number of these. We have proved only that the intersection of a finite number of subsets of M possessing IP of I also possesses IP of I, not an infinite number of subsets of M. However, it turns out that M1 still possesses IP of I, so the rest of the above proof still holds. So this is what we finally have to prove, that M1 still possesses IP of I. Here we go. Let S1 and S2 be any two states such that S1 and S2 are the same on M1. In order to prove that M1 possesses IP of I, we have to show that S1 prime restricted to OR of I equals S2 prime restricted to OR of I, where S1 prime and S2 prime are as we've always defined them. By axiom 2 above, S1 and S2 are different only on a finite set, which we're going to call M2, of variables. Let us call these variables x1, x2, and so on up through x sub n. So M2 is the set consisting of x1, x2, dot, 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 up to xn. Okay? Clearly, no variable can be in both M1 and M2. If z is in M1, then S1 of z is equal to S2 of z. If z is M2, then S1 of z is not equal to S2 of z. Therefore, each x sub I is not in M1 for I equals 1 through n. However, M1 equals IR of I, just as in the case of M being finite. Therefore, each x sub I is not in IR of I, for I equals 1 through n. By lemma 3 above, then, M minus the set consisting of just xi possesses IP of I, for each I from 1 through n. What is the intersection of all these M minus the set consisting of just xi? There are only a finite number of these. It does not contain any of the xi, but it does contain every other variable in M. Therefore, it is just M minus M2. whereas before M2 was equal to the set x1, x2, ... up to xn. By the corollary above, this intersection of a finite number of sets, each of which possesses IP of I, also possesses IP of I. So M minus M2 possesses IP of I. But S1 restricted to M minus M2 equals S2 restricted to M minus M2, since S1 and S2 are different only on M2 by definition of M2. By the definition of IP of I, then, we have S1 prime restricted to the output region equals S2 prime restricted to the output region, where S1 prime and S2 prime are defined as above, and that's what we had to show. And this completes the proof, finally. There are lots of other theorems in computer theory. All of them can be proved using just axiom 1 and axiom 2. So all of these hold for all computers. If you've ever heard of Bernstein's conditions, these are some of the things that can be proved in this way. My paper on this is called A Theory of Computer Instructions. It appears in the journal called Science of Computer Programming, May 2006, pages 244 through 273. Thank you very much, and I'll take questions.
Thank you so much, Dr. Moore. Thank you for taking the time to coming in and doing this. Even though, again, this is a pre-recording, this was due to some scheduling issues. So after watching this webinar, which was very informative and very intelligent, if you all have any questions, please go ahead and forward your questions to Dr. Moore through the email address provided on the slide, and that is again moore@email.gwu.edu. Thank you so much, Dr. Moore, for your time, and thank you all for watching. Goodbye.
Goodbye.